Okay, let me start by the brief reminder what happened last time. So we considered a definition of this pi1 of X, topological space X with some fixed base point. And so we carefully defined it and checked that the definition is self-consistent. So this is, there was some verification that this, the loops, the homotopy classes of loops at a point, they form a group. And then we check that for path-connected topological space X, if you consider fundamental groups defined for two different base points, they're actually isomorphic. Up to isomorphism, this dependence on the base point can be dropped. And then we also considered a definition of the covering. So covering for some topological space X is a pair which contains another space X tilde and P, the map which is called projection, which so that morally, intuitively, one can understand X tilde, this construction as X tilde is locally looks like number of copies of X. Informal statement one can keep in mind. So why is this the case? Because by definition, this P and X tilde, they satisfy this following property. So any point in X in our space in the space capital X, by definition, there was required that there exists some neighborhood, open neighborhood, and this is why we can understand this locally, open neighborhood, so that the pre-image is a bunch of disjoint union of open spaces. Each of them is homeomorphic to this open neighborhood for X. And this homeomorphism is provided just by restriction of P on each of these on each of these components, disjoint components in the pre-image of this neighborhood of X. So this means that locally, this space looks like a bunch of copies of this space here at the bottom. Okay, and so we started. We formulated the following proposition, which we are now going to prove. So that remind you briefly the formulation. So last time I wrote formulation in words, but I also wrote the following diagram, which summarizes the statement of the proposition. So we have a logical space X, and we fix its covering with some projection P, and then we consider a certain map from another topological space Y times an interval to X, that is denoted by F tilde. And we also can consider the copy of Y included in this product just by considering Y times a 0 point here. And what we know is a restriction of F on so we consider a lift of restriction of f on this y times 0 here, which is we denote by f0 tilde. So this is a lift of f restricted at 0. I remind you, by lift we mean something, so if you have a map from some space to X, the lift of it, it's a new map to a covering, so that if you compose it with projection, we get the original map. And then you want to make a statement about existence of a lift of f itself, which we denote by f tilde, once all this f tilde 0 is fixed. And the statement that there exists a unique lift f tilde of f once we fix the lift of this restriction at one of the ends of the interval. Any questions about this last lecture material? Okay, the proof will be a bit tedious. It will require some analysis. So what we want, so let me draw a picture here, for example. What do we have? Kind of schematic picture. We have y times an interval. Here, this is the interval. Imagine it looks like this, some sort of cylinder. And what we want to take some point. Let's fix some point. Let me draw it y here. Point, let's say y 0 my space y. And so we consider the map of space, this product space f to x. Let this the image of y0 let me also fix a point t in the interval. Where here will be a point, the product y0 comma t. And then we consider an image x0, which is the image of this point under our map f, which is given to us, like this. And since by definition of a covering space, we have a covering space x tilde, by definition there exists for each point x, there exists what is called evenly covered neighborhood, which will be denoted by x, u0 x tilde, which we can choose. So let me write it in words. So we want to take x0 in y again and t in the interval. This, or maybe I shouldn't, yeah, I'm just repeating what I already wrote. And so we know that there exist evenly covered open subset containing x0, which we know by UX0. This contains X0. And we also can use the fact that F is continuous function. Again, all our maps which we use seem to be continuous, and then it follows they exist it follows that there exist open neighborhood shown by n in Y containing the point Y0, so it looks something like, take a color chalk. N. And also some interval, some sufficiently small interval with endpoints which are AT and BT, which contains T. So this is a open subset in our interval 0, 1, so that such that this product F of the product of this interval, this image is contained entirely in my UX0. Why is this the case? So n times t looks something like this. This is the product of a neighborhood of y here and an interval here. So why is this the case? So this is so since f is a continuous function, we can always find a sufficiently small open neighborhood of our point here in our space from which the function acts, so that the image is contained in UX0. So this is just a definition of continuous function. But since we have a product topology here on y times interval, this we can always assume that this neighborhood of our point is of the form of a product of neighborhoods by taking them again to be sufficiently small. So this this neighborhood, which has a form of neighborhood here times 0, 1, it looks like kind of a cylinder. Is we take it sufficiently small that its image is entirely inside our evenly covered neighborhood of X0. So we make these choices. And now we notice the following. So we can consider, we can do this for any point. Let's fix y0, and we can do this for any value of t, right? T was chosen to be arbitrary. And all such intervals here, they cover our interval from 0 to 1, right? Of course, in principle, yeah, let me mention that I can also, if this AT and BT can be allowed to be 0 and 1, but if it's 0 and 1, then of course I have have to consider the, I have to include the boundary here. So this can be also of the form 0 bt and principal and AT comma 1. Because this should be an open subset in the interval, which is a intersection of the interval with open subset on the real line. So these forms, all these intervals, they form for all t, they form open cover of our interval, which we know is a compact. So we can choose a finite subcover. So this interval is compact. And this means that there exists a finite cover by intervals of this form AT, BT. Again, if AT happens to be 0, I actually have a square bracket here, and if BT happens to be 1, I actually have a square bracket here. So for some finite, so it's sufficient to consider a finite number of points t. So the corresponding intervals, they completely cover my interval from 0 to 1 because of the compactness. And but so this is not very convenient for us. What we want to do is so from this construction, we want to obtain slightly modified cover. We want from this statement, it follows the following slightly modified statement. There exists a finite number of points ti inside these intervals. So they are ordered. The initial point, so initial point coincides with 0, and the final point coincides with 1, such that and a new, possibly new n, a neighborhood of y0 in y, such that for any I, the image of the interval from ti to ti plus 1 times n is inside some ui, which is evenly covered. How does one passes from this statement, where we have a kind of finite cover by open intervals, so that for each open interval we have a, so originally this nt was depending on choice of t, possibly. And so how this happens is that, how does one goes from this statement to this one, is that we just take ti's such that each closed interval between two consecutive points ti is inside some of those open intervals which we had before. This is for some t. And we take our new n to be intersection of all n's in the open cover. before we have a finite cover by open intervals corresponding to some values of t. And for each value of t, we have some fixed n. So that this product of open interval here times n was inside then some evenly covered neighborhood of x. And then what we do, we can only to get an open cover, we can only restrict to a finite number of such t's. And what we do, we just we can always fit our kind of small. We can choose these points ti, so the corresponding intervals are inside some of the open intervals which we had before, and we take n to be intersection of all n's which we had before. Is this step clear, or are there some questions? Okay, it's clear. So now we have a bit different picture. So now we could have a little bit different picture. We have this again, a product of y. Y times an interval, so that we fix. Now there is a neighborhood of y0 which fixed some new, possibly new neighborhood n, which we constructed as described here. And then there is some, we have some division of this interval. Like this. This one is Tm, 0 was T0. So that we consider a pair of points Ti and Ti plus 1, and we can consider product of this closed interval times n, which can be imagined to be looking something like this. And we also consider Ti minus 1. Let me write. These are all copies of the same neighborhood n for some fixed value of t. And what we know is that for each of these intervals, we can consider a product of this closed interval times this neighborhood n, which fixed the same for all i's, so that in x, we can consider is mapped to x. This is this image its image belongs to some evenly covered UI. Let me denote this UI in blue. Now what we want to do, we want to construct this lift of f lift f tilde section of the lift on this n neighborhood in y times an interval from 0 to ti for some I should be a lift of our f restricted to n times interval. And we want to do this by induction. With respect to I. So first we consider the case I equals 0. So this, but then we know that f, then we just take f when this, we know that t0 is just 0. So we have just n times a 0 point, and we just take it to be f tilde 0, which is given to us. So we already know by the statement of the proposition there exists given to us lift of f restricted to 0 at the interval. So we just take it this thing, and then this is a base of our induction. Then we need to consider induction step. So suppose we have we constructed lift from for some I, and we want to construct a lift for I plus 1. How do we do this? So we know that f. So by our choices made the image of m times interval from ti to ti plus 1 belongs to some some evenly covered ui. So essentially what we did, we constructed the lift of the function up to here. We assume that we constructed the lift up to here, using that in the beginning we already have lift of the function defined on this t equals 0 slice. We constructed the lift up to here, and then we are looking, we want to lift it, construct a lift of the function on this neighborhood. And since this UI is evenly covered, there exist this means that in particular, if you consider image with respect to projection map from X tilde, image looks like a disjoint union open sets. Each of them is homeomorphic to U. And let's suppose since we constructed the lift up to here, so this is the value of f y0 I. We know, we already know the value of f tilde y ti somewhere in X tilde. And of course, it contains in one of these preimages. Must be in one of these preimages. And let me denote particular this disjoint so we know that the whole preimage contains a disjoint union of open sets. Each of them is a copy of this, essentially a copy of this UI, and this f of yti should belong to one of them, which we denote by this ui tilde. And so there exists a unique ui tilde in X tilde such that this restriction of P, our projection on this ui tilde, provides us with a homeomorphism to ui. And f, so I'm just writing what I said in words before, and f of y ti tilde is an element of this ui. It's uniquely determined by because they're all disjoint. So it can belong to only one of them. In principle, if you want more explicitly, one can write the preimage of ui is some a bunch of disjoint union with respect to some index alpha ui alpha. And this ui tilde, which we chose, is u alpha I for some alpha, is determined by this condition. You know, because we know that this is this fy0 ti should belongs to this, right? Because it's a lift of f whose value is in ui. Okay, and so we fix this open subset in X tilde, which is homeomorphic to ui tilde. And then what we do, we just define f tilde restricted to n times I plus 1 as so since the restriction of P on this ui tilde is a homeomorphism, we can invert it by inverse restriction of composed f function which is given us to this interval. This is because once we fix this ui tilde, this P inverse, we can consider P inverse restricted to ui tilde, and it will be a homomorphism from this ui to ui tilde, and then f tilde. Then we define. So again, we defined f tilde up to here, and on this new kind of on this new interval, to extend it to this interval, we just define it by considering this composition of f and P inverse. It's defined as a lift on this on this new small interval. And then we continue by induction. We continue it so on, and starting from this way we can define it the lift, extend the lift to the whole interval. Induction. Have there exists a lift. We constructed a lift. The whole interval times our neighborhood n on lift of f. And this can be using the commutative diagram. One can write it like this. So we have n times interval. We have f. Some space here. So we have f restricted on this neighborhood times an interval. And what we did so far is we constructed a lift tilde for this restriction only to the neighborhood. Now what we want is to extend it, because we want to extend it to the whole y to prove the statement of the proposition. But are there any questions so far? Before extending this to the whole y, we want to show that following intermediate statement. If we assume that Y is just a one-point space, so in this case we already constructed the lift. It was just this is just a one point. Point just containing Y0. Then F tilde is unique. To show this, let us take any other lift. Let's say F tilde prime, and show it, and we'll show it that it's the same function. And again, we will show it by induction. So assume by induction we will show that first show that on the interval from 0 to Ti, this some other lift which we consider coincide with the lift which we just constructed. And so again, what happens for the base of induction when I equals 0? Well, this is trivial again because well, we just have a requirement that the lifts should be the same as F0 tilde, which we have, which is given to us, right? This restriction to the just to the 0 on the interval. And then about induction step, so we assume that they are the same for some I, and we want to show that they are the same for when instead of I we have I plus 1. Again, so by F tilde which we constructed, it satisfies this property. So now Y is just, I don't write Y here because this is just a one-point space. So F tilde on the small interval from Ti to Ti plus 1 belongs to Ui tilde, some open set in the preimage of Ui, which we fixed before. And so we know that so here just one point. So we know that the lifts they coincide up to Ti. So the same. And in particular, they should coincide. Yeah, they should coincide at this point. And since they coincide at this point, they both have image, the same image. Point, right? Same as F tilde prime Ti, because they coincide here, and this means that if so first we know that now we consider the image of F tilde prime of the full interval here. We know that if we compose it with the projection, it should still be inside our evenly covered neighborhood. So this means that F tilde itself is belongs to the preimage, our UI. So it should belong to one of these copies of UI which we have here, one of these UI alpha for in this decomposition, disjoint unit decomposition of the preimage, right? We know this should belong to only one of them because this is a continuous function, and this interval is connected. So use the fact that this is connected. So the image of the connected space cannot belong to two disjoint open spaces. Right? It should be contained only in one of them. So since this is a union of disjoint sets, alpha I should belong completely to only one of them, and here and this one of them should be the same as we had before, UI tilde, because we know that at least one point is mapped to this open set. Since follows that f tilde prime interval is completely inside this u tilde I. But if we restrict ourselves to this interval, the projection is homeomorphism, so it's invertible, and this means since this is composition, sorry, or what I want to say is that this is it follows that tilde restricted tilde prime restricted to the interval is given by inverse of p restricted I tilde composed F. Because we know that by definition the lift is such that if we compose it with P itself, it should give us F. But on this subspace, we can invert P, the restriction of P. That's why we can put P inverse here. But we also know that this is by construction is just the same, so restriction of F on Ti plus 1. We also know that by construction, this is the same as F tilde, which we defined before. So they are the same, these lifts are the same or restricted on these intervals. So this proves us the induction step. And it then follows that F tilde prime is the same as F tilde on the whole interval 0, 1. This is, again, this was the case when the Y itself was just a one-point space. Okay, now we are almost done. What we did so far is that we constructed a lift for arbitrary y. We constructed a lift on the of f on the neighborhood of any point of y times an interval. And the other thing which we did is that if for just a point, we also proved the uniqueness of the lift. Now what we want to do, we want to consider general y and to show essentially simultaneously that the lift exists for the whole y and that it's unique. So what we do is first we construct lift of f lift f tilde of f for a neighborhood n of any point y in capital Y. So this is we know how to do. And then we notice that they all agree. So we have a lift for neighborhood for each point. They all agree on the, so for each y we consider neighborhood, we construct lift there, so there can be multiple y's. We consider each point, for each point we have a neighborhood, but they all agree because so meaning that the restrictions, if we consider a pair of points y and y tilde and the corresponding neighborhoods n and n tilde, that the restriction of the lift on the intersection of these neighborhoods is, for example, necessarily the same well, it's maybe not a good notation, but let me choose a bit different language. Y, we have some point, let's say y1, it's some neighborhood n1 for which we construct a lift f tilde, let's say 1. This lift of the f restricted to this neighborhood times an interval, and then we do the same for y2 and n2, and here we define a lift f tilde 2, and they agree in the sense that f tilde y restricted to n1 intersected n2 is the same as the restriction of f tilde 2 on the same intersection here. And this is the case because of the uniqueness of restriction to any point so we know that we can consider a restriction of these two lifts at any point in the intersection, but we already showed that the lift restricted to a point, just a point in y, is unique, because we showed this is the case when y is just a single point. This should all agree, so this can be used to just define f everywhere, the same f everywhere. So this gives a well-defined lift lift f tilde full space y times. For any, if you want to consider any point on y, we can use any lift which we define for any neighborhood. Doesn't matter, they all agree. And of course, it's also unique because it's unique. Its restriction to any point is unique. This finally proves our proposition. Any questions? Again, the idea, as often happens in this kind of true proofs in topology, is that we kind of consider a small, consider first everything in small neighborhoods where everything is nice and simple, because we know that on a small neighborhood, this x tilde is just a bunch of copies of x itself, and here it's easy to fix the lift just by using this homeomorphism. And then we just have to work a bit to extend it to everywhere, from kind of local lifts, lift defined locally, to a global defined lift. So we will need the following two corollaries of this proposition. First, corollary 1. For any path f x and fixed point x tilde 0 in the preimage of some point x0 under projection, where x0 is the image of f0 x. So it's understood as so here we just consider, let me write it like this, maybe we consider our space x, lift tilde. So we have a path f starting at x0. There exists a unique path f tilde in the covering space tilde such that it starts at x0 tilde. So it follows immediately from the proposition that we have before for just take y equals, again, one point space, right? Position. And as this is a fix of lift this fix of x tilde 0 is just a fix of the restriction, fix of the lift of the restriction of f on this point 0 here, which is has a meaning of the initial point of our path. Once we fix the initial point, this path has a unique lift. In X tilde. So one can illustrate this by considering this example of the covering space which we had before. So the covering of S1 by R, which is given by the map which sends T here to T 1, real number. And so this can be imagined as kind of R being some sort of spiral in a three-dimensional space. And this projection is just a projection to a horizontal plane where S1 lies. And there's some path. I fix a point, some point here, x0. And so it has multiple preimages. But if we fix one of them, let's say x0 tilde, and now we can see the path f going, for example, somewhere like this. And so anywhere, so once we start, anywhere locally there exists a unique lift, but this can be continuously built globally. So for example, here lift goes like this, but if you, for example, consider a path which goes something like this, the lift from this, in this example, it's kind of obvious, intuitively obvious that the lift is uniquely defined once we fix the initial point. Second corollary which we'll need is the following. So for any path homotopy is, as you know, path homotopy is a map from a square, topological space X, and a fixed again we fix x0 tilde image of x0, where well, x0 is a initial point of the path between which we can see the homotopy. So this is equal to f 0t point et. There exists a unique path homotopy f tilde our covering space x tilde of so there's a path homotopy of paths starting at x0 tilde and lifting f tilde is a lift of our f. The proof essentially follows again from our proposition for y, now y being an interval itself. But there is some subtlety which one should address. So the subtlety is the following. So of course we fix. So in X itself we have a pair of paths F and let's say G, between which this pair we have some homotopy F, and which we want to lift. And so you can lift, so of course there is, again, we already know that there is a unique lift F tilde which exists, and there also similarly unique lift of G tilde exists. And of course we know that this function F, so since we already fix, so what we want to do, we want to, what we do is that we fix so this is a, let's say this is a homotopy parameter, and this will be y. So the restriction. So we know we take the restriction of the we know the restriction of the lift at 0 here. So this is just a constant map to x0 tilde, our fixed point in the covering space. And this then the proposition directly tells us there is a lift. There is a lift of F tilde such that it restricts to a constant map to x0 at the at 0 here. But it can happen. We know that the homotopy, we don't know if it, and it gives you some homotopy between F tilde and G tilde. But we don't know for sure that this is a path homotopy. We don't know because this endpoint of G tilde might happen not coincide with the endpoint of F tilde here. We need to check that these are actually the same points. So more precisely, we need to check that F one T tilde is constant. We already know that F0t is constant because it's equal to x0 tilde for any t by construction, since it's with this notation, I'm sorry, actually I have to assume that this y is this. There's some subtlety which interval is which. Yeah, this is y. Y is the second. No, it was a k. Yeah, let me use the proposition. Yeah, we'll use the proposition when y is a second interval, which correspond to yeah, it's easier to do this way. Let me use the proposition when y is a second interval, which corresponds to a homotopy parameter, and this interval is a path parameter. Then we know we use this as our f0 tilde in the proposition, which is fixed to be a constant map to x0 tilde. So then using the proposition, we know that there exists a unique lift of f tilde. And what we want to check that this is actually a path homotopy, is that this is also constant. So this point, in particular these points, they actually coincide. And how do we check this? So we check this by noticing that noticing the following. Erase this. We know that f, where the first argument is restricted to 1, and kind of the second argument we keep on open, so we consider this as a function from interval to y. And we know that this is function, since we know that f is a path homotopy, this function is constant. Is equal to f1. This is the end point of our path, which we consider, and the same as g of 1. Terminal point of both of these paths is constant, and if you just consider this function, it has a unique lift. This function has a unique lift. By constant. If we fix for example, f as a value at the end again. So this is if you fix f1 the lift at 1, 0 by constant f tilde. Well, maybe it's better to use maybe another. Let me note this another function. Just we consider this is just a function. One variable. Lift, as unique lift g tilde. We fix g tilde of 0, and with this we fix to be our f tilde 1, 0. So we already have some lift f tilde 0, f tilde, and we fix. Now we consider this as a function of just from interval to x, and we fix g0. We want to lift it by some lift g tilde, and we fix g tilde of 0 to be the same as f tilde of 1, 0, and we know that the lifters exist, and it's unique, and we also know that one can lift it by choosing just so since this is constant, one can lift. There exists a lift by again a constant. By a constant function. which is the same. Which, but there also we also know that there exists a lift by f tilde 1 comma t. This also lifts this function, but by uniqueness they should coincide. And by uniqueness, this f tilde of 1 comma t, it should be also constant. And then it follows that indeed f tilde is a path homotopy. Not just arbitrary homotopy, it's a path homotopy. So this proves our second corollary. Again, the subtlety was that is checking that this is a function. So we have a path homotopy which is a function from a square towards pi x, which satisfies the condition that two sides of the square they actually all mapped to a single point, so this restriction are constant maps. And so we already know that there exists a lift of this fixed condition at one side of the square. And the only thing we need to check that once we lift the other side of the square is actually also lifts the restriction of f to the other side of the square also lifts to the constant. So the lift is actually path homotopy. Any questions about these two corollaries? Now we are ready to prove the propositions that I formulated before, that the fundamental group S1 is isomorphic. Well, I will probably, I'll start the proof by telling the idea, and then you will have to finish it next time. So again, the idea is to construct explicitly a map from pi1 from the fundamental group to the group of integers, and to show that this is isomorphism. This is the map constructed as follows. Again, this is a group of equivalence classes of loops. So we consider, for simplicity, loops based at 0 modulo 1. Again, here we understand S1 as real line modulo integers. So the points on S1 are the numbers modulo 1. So we take the base point to be the class of 0. And so we consider a loop in S1 based at this point. So that F0 and F1, the initial and terminal points are 0 modulo 1. Here is 0 modulo 1, and the map from interval to S1, which satisfies this condition, it looks like a path which goes somewhere like in the circle and comes back to this fixed point. And then using the corollary 1, we know that there exists a unique lift F tilde to our covering space R. So we have a map from interval to S1, and projection from R to S1, which is just taking the numbers modulo 1, map F, and we know how to construct F tilde given, so this is a lift of F with fixed initial condition that let us choose F tilde of 0 to be, so we have to choose it in the preimage of initial value of F itself. And we can always take to be 0 in the real line to be our initial point. So 0 is, of course, in the preimage of 0 modulo 1. And so this gives some path and in R. And we know that, so this is a lift. So in particular, we know that if we take the value of our lift at 1, and then take a projection of it, F tilde is valid in R, and projections send us back to S1. This should be the same, since it's F tilde is the lift of F, this should be the same as the value of F at 1, which is, we know, is 0, right, by our construction. But this means that, so if the projection is just takes our real numbers modulo 1, so this follows that, and since it's a 0, this follows that F of 1, F tilde of 1 is an integer inside R. And then this is some integer value, and we will use it to define our map. We define map from y1 to z. So this is a voice point mod 1. So that the class of the loop F, which represents elements here, will be sent to F tilde of 1. And next time we will show that this map is actually well defined, so it depends on the choice of representative, and it actually gives us isomorphism between these two groups. But the idea is that, so we have a F is a loop in S1, which kind of winds some number of times here. And this, we want to define precisely what this number is. And this number will be actually the number which we get after lifting this loop to R. If we fix the initial point of the lift at 0, we show that look, the number of times this we wind here along S1 it will be the same as the number of kind of floors on the spiral we go up or down. And this is exactly the number which we get here by considering f tilde of 1. But yeah, for today it's I finish here, and next time we will continue the proof. Are there any questions? I remind you that the next lecture will be only in a week because of these Salam distinguished lectures on the second half of this week. But I think you still will have tutorials on Thursday. Okay, if there is no questions, that's it.